Example 3, simulating projectile motion in the calculator. It says a distress flare shot up 85 degrees from a ship's bridge, 75 feet above the water, with an initial velocity of 76 feet per second. Graph the flare's height against time, get the height of the flare above water at each time, and simulate the flare's motion for each length of time. So basically, very simply put, you have some ship out in the ocean. I'm a terrible artist, but here's my ship, and it's got some cannon, and it launches something off the ship's bridge like this. All right, now we want to graph and measure this over time. And here's what we know. When it's shot up, it is shot not at the ground level. It's actually shot, or sea level rather. It launches from somewhere up here, and they call this a height of 76 feet. So from wherever the bridge is that they actually shoot this off of, it is 76 feet above water. All right, and to make this more realistic, I'm going to move this down a little bit so that that's from there. Okay, and so we shoot from a height of 76 feet. And not only that, well, whenever we shoot, it actually comes out like a vector. So this comes out straight like this, and it comes out at, it says 76 feet per second. I just realized I put the wrong value here. This is actually 75. This one's 75 feet. This comes out at 76 feet per second. And it comes out at a certain angle. The angle that this actually launches at is, and let me move this down so that we can, let me move that right there. There you go. This angle that it launches from is 85 degrees. Now we want to know how far it travels. So what we're going to do is I'm going to use my formula chart, and over on the front page we have it listed right here when you see in projectile motion these two equations. All right, so we're going to use these two equations to graph this in the calculator. So the two equations are that x equals v naught times cosine of theta multiplied times time, and the y equation is negative 1/2 gt squared plus the initial velocity v naught times sine of theta times time plus the initial height. Now g is gravity, and g has two values according to the formula chart. It can be 32 feet per second squared or 9.8 meters per second squared. Our equation is talking in feet, so g is going to be the 32 feet per second squared. And actually SEC, but there we go. So let's plug in what we know. We know in this problem that the initial velocity is 76 feet per second. So I'm going to come over here and replace this with 76 feet per second. Now we also know our angle is 85 degrees. So I'll come here and type in 85 degrees. It goes there and there. Finally, we know the initial height is 75 feet. Let me get that in. I forgot about that one. And then gravity. On this problem, since we're talking in feet, it's going to be 32. And so this g would get replaced with 32. Anytime we substitute, we're going to use parentheses when it's in between things like that. So there's our equations. So let's go to our calculator and have it calculate all this for us. So we go to menu, graph entry, choose parametric, and my x equation was the initial velocity, 76, times cosine of that 85 degrees multiplied times time. Underneath we had negative of 1/2 times g, which is 32, times time squared, plus, we have another parentheses. It's kind of like right up above, but we change this to a sine because we're now talking about the y value of 85 degrees. And finally, we put the t out there, and then plus the initial height, which on this problem, we were launched from 75 feet up in the air. I hit enter, and I don't see anything. That's because that's so far shifted up. So when I go to Window, Zoom Fit, this shows my launch. Now, it asks a couple different questions. Over here, we're asked to find what are the values at these heights? So what I can do is I can come back over here and get the table. The table will give me the exact height. So if I press Control T, notice that it puts the time values here. This would be the horizontal distance, and this would be the heights. I can check to make sure it is looking for heights. Let's see, graph the flares, height against time. What else does it say? Let me move this down here. Graph the flare's height against time gives the height of the flare above the water each time and simulate its motion. Okay, so we are looking indeed for height. So I come over here, and it'll be this value is the y value, this is the x, this is the time. And so these will be the values that I need. So I'm going to just copy this picture real quick. I'm going to move it over here. And now that we have this picture, we can now get our answers. The height at 1 second is over here. It's 135 feet if I round, 135 feet. At 2 seconds, it would be 162 feet. At 3, we don't need 3 seconds, so we go to 4 seconds. I get 122 feet. And finally, 5 seconds would be 54 feet, which means it would be below the deck of the boat. So if we shot, if that's the deck of the boat, it would be below it. So on my boat, I should have added something up here, some stand or whatever to represent where the cannon is. That's how you would solve this one. Let's try another one. Let's try part B here. It says Kevin hits a baseball 4 feet above the ground with initial speed of 150 feet per second at an angle of 18 degrees with horizontal. Will the ball clear the fence 399 feet away if the fence is 5 feet tall, if it's 8 feet tall, or if it's 12 feet tall? Let's see. So here's Kevin. He's hitting, and so he's got his bat out here, and as he's swinging, he hits this baseball, and it flies off the bat. Now, it comes off like a vector. But we know that it actually, when you consider gravity, though it comes off at this like this, it'll go and make a parabola kind of like that. Now, we know that this fence is going to be 399 feet away. So if we go out here 399 feet, which this is an x value, we want to know what is the height there. That's what we're looking for. We got to figure out the height. So let's write this as an equation. If you remember, our two equations are x equals the initial velocity times cosine of some angle times time. That's a parenthesis there. And then here you have y equals negative 1/2 gt squared plus almost the same question as above with the t. And again, this is a parenthesis. Both of those turned out ugly. Plus y, the initial height. So let's go. First thing it says is he hits the ball 4 feet above the ground. So this here is 4 feet. That goes in right here. That's our initial height, 4 feet. Now we come back to the problem. The second thing it says is the initial speed of 150 feet per second. So the ball comes off at 150 feet per second. So when I go, that's the V0, the initial velocity, V naught. So that's 150. This is 150. So 150 and 150. It says it came off at 18 degrees. So this angle here from the horizontal is 18 degrees. I'm going to make sure that it was 18 degrees. So I now fill that into the equation for theta. We have 18 degrees. And finally, gravity. Since we're talking about feet, we're going to use the number 32. So instead of here, we go to 32. And that's what we're going to plug in. For the sake of time, I'm just going to pause the video and type in the new value. All right, so here's the fly of the ball when I typed in these equations. And so now what I want to check is, what happens at 399 feet away? So I'm going to go to graph, trace, and I'm going to look, and here I'm looking at 399 feet away. So there it is, exactly 399. What happens at 399 feet? Well, we can see that it has a height of 8.5 and a ball's been in the air for 2.8 seconds. So what do we want to know? Will it clear a fence that's 5 feet tall? Well, considering that the ball is 8.35 feet, 399 feet away, yes, it will clear this fence. It will clear Well, if it's yes, it'll clear this one, so it'll be a home run. Will it clear at 8 feet? Yes, it will, by about a third of a foot, just about 4 inches it will clear. But will it clear something 12 feet tall? Answer is no. Why? Because at 399 feet, we have a height of 8.35 feet. And in case we were wondering, t was equal to 2.8 seconds. That's how long it took for this ball to get there.